Now the reaction is now balanced. If you count around boron, you have 1, 2, 3, 4, 4 bonds. If you count around nitrogen, you have 1, 2, 3, 4, which is 8 electrons in their outermost shell. Now, most Lewis acids are used in catalysts for aromatic substitution reaction, and they include, of course, you've seen boron trifluoride. Aluminium trichloride is also a Lewis acid. So you may be asked to give examples of Lewis acid. Aluminium trichloride is one of them. Are you getting it? Then boron trifluoride is one of them. Most positive charge ion are Lewis acid. Most positive charged ions are Lewis acid. Is that okay? So all these are examples of Lewis acid that are used for most reactions. I told you that aluminum trichloride is used as a catalyst for aromatic substitution reaction, which I believe you have done before, for aromatic substitution reaction. It is used as a catalyst for aromatic substitution reaction. Is that okay? Exactly. All right, let's see what we have next. Relative strength of Brustolurix acid and base. Degree of dissociation. Now, a strong acid will have a higher tendency to dissociate, to form hydronium ion, as compared to a weak acid. Now, the definition of strong acids and weak acid, I believe most of us know, is that strong acids are substances that dissolve in water to dissociate completely in water, while weak acid are substances that dissociate only spiraling in water. When we say only spiraling, we mean they dissociate slightly or partially in solution, while strong acid dissociates strongly in solution. Are you getting that? So a strong acid will have a higher tendency to dissociate, to form the hydronium ion, as compared to a weaker acid. Hence, the degree of dissociation of acid, the stronger the acid. Now, the higher the degree of dissociation of the acid, the stronger the acid. So acid that have a higher degree of dissociation are stronger than acid that have a weaker dissociation in water. So when you dissolve an acid in water and it dissociates completely, it means that acid is a strong acid. While if you dissolve an acid in water and it dissociates only partially or spirally, you say that acid is a weak acid. For instance, if you look at this, acetic acid is a weak acid compared to HNO2, compared to H2SO4, compared to ACl. So HCl is a stronger acid as compared to H2SO4 negative. Why the acetic acid is the weakest of all those acids that are listed there. Is that okay? Now, however, the strength of base depends on the ability to form the OH ion in aqueous solution. That is strength of base. Depends on the ability of the base to form what? OH ion in aqueous solution. Now, a higher or a stronger base will have a higher degree of dissociation than weak base. So when we generally talk about the strength of acid and base, is dependent on their degree of dissociation in water or in solution. So why a strong acid will dissociate its solution to form H plus ion, a strong base will dissociate in solution to form OH negative ion. Is that okay? Now the bases are in the order of NO2 is less than this, the acetate ion less than ammonia. So in this case now, ammonia is the stronger of bases as compared to others. Look at this very well. Now, acid and base, dissociation constant Ka and Kb. Now consider a weak monoprotic acid. Now when we talk about monoprotic acid, is an acid that can only give out one proton. It's called monoprotic. For instance, HCl is monoprotic. Are you getting it? HNO3 is monoprotic. Reason being that this acid, they can only give out what? One proton. This one can only give out this. This one can only give out this. Or more like the basicity, we have monoprotic. Also, CH3, COOH is monoprotic because it can only give out this H here. Now, however, Another compound that is also, if you look at H2SO4, this one is diprotic. It can give this H2. If you look at H3PO4, this one is what? Triprotic or triprotic or polyprotic. You can say poly. That means it has more than one or more than two hydrogen ion it can give out. So consider a weak monoprotic acid which dissociate partially in water like this. This reaction, you consider HA as the acid. So this is an acid HA plus H2O. Now my dear students, listen. If this is an acid, it means that this one is capable of what? Donating proton here. If you donate a proton here, what are we now going to be having? Proton plus this one will give us H3O plus. Why does it become what? A negative. Now at equilibrium, there's what we call the equilibrium constant expression. The equilibrium constant expression is often represented with Ka. Now the equilibrium constant expression is in such a way that you write the concentration of the product all over the concentration of the reactant following the law of mass action. Now if you don't know what the law of mass action is all about, you should go and browse about it. Following the law of mass action. Alright? Now at the end of the day, when you do that, I told you that you are going to write the concentration of the reactant all over the concentration of the product following the law of what? Mass action. So how do we achieve that? Your Ka, look at it. Let me put it here. Ka will be concentration of the product. The first this you have here is H3O positive. Now when you use bracket like this, you are talking about concentration. There you have A negative concentration divided by that of the reactant. Now the reactant, as you can see, you only have HA there. You don't have H2O because pure liquid and pure solid do not show in the equilibrium constant expression. Reason being that their concentration does not change during the course of the reaction. Their concentration do not change during the course of the what? Reaction. Is that okay? Their concentration do not change during the course of the reaction. So pure liquid and pure solid do not show in the equilibrium constant expression. H2O is a pure liquid. Now the only thing that show are aqueous solution. For instance, aqueous solution are gases. HA is aqueous. This one is aqueous. This one is aqueous. The reason why you say they are aqueous is because they are already dissolved in water. They are substances dissolved in water. Like H3O plus, they are ions dissolved in water. A minus, ions dissolved in water. HA dissolved in water. It's an acid dissolved in water. But pure liquid, that means water is pure. And pure solid do not show in the equilibrium constant expression because their concentration remain constant during the course of the reaction. What we only put in the equilibrium constant reaction are those substances whose concentration change during the course of the reaction. Now the higher the value of Ka, that is the equilibrium position is most towards the right hand side, the stronger the acid. Now how do we have a high value of Ka? Is when we have more of the product. True or false? Because it's when the upper side is higher, that's where we have a higher Ka. Alright? So the higher the value of Ka, that is the equilibrium position is more towards the right hand side, the stronger the what? The acid. So the more the H3O positive that is formed, the more the what? The stronger the acid. Are you getting it now? That's why we said there are substances that dissociate completely what are strong acid. Now as you can see, a strong acid will form more of what? H3O positive. It's true or false? So that's why we say the higher the Ka value, that is the equilibrium position is moved towards the right hand side. When we want to calculate the equilibrium position, you discover that if this value here is very high, the equilibrium position, let's take for instance, if the upper part, which is the product, you know the product is what we have on top are B, you know the product is what we have on top are B, good. If the product is what we have on top, if here is like 20 and let's say the under is 2, 20 divided by 2 will give us what? 10. Now let's assume the upper part is like 10 and 10 divided by 2 will give us what? 5. So which of them have a higher Ka value? It's not the one where we have more of concentration of the what? Of the product. In this case 20 divided by 2 to give us what? 10. That means Ka is 10. Why Ka is what? 5. Weak base which dissociate partially in water. So if they ask you to write the dissociation of acid in water, this is the reaction you are going to write. Whenever you hear of dissociation of acid in water, this is the only thing you are to write. Alright, so if you hear of dissociation of acid in water, this is the equation you are to write. Is that okay? Remember, this equation is very, very important. Why if they say dissociation of base in water? Now, as you can see, that for the acid, this one donates a proton. Why for the base, the water act as the what? Acid. That means it donates a proton. Are you getting it? For the acid donates a proton. Why for the base, the water donates a proton. For the acid donates a proton to the water. Why for the base, the water donates a proton to the base. Note the two difference. Are you getting it now? Because we said acids are proton donor, while base are proton acceptor. So in this case now, this one is donating a proton to the base, which the base is what accepting. So if you donate a proton here, what are you going to have? H plus is coming here, plus the B here initially give us HB plus. Then what will be left here? Of course, you know OH negative, which is the OH negative. So when they say equilibrium constant for base reaction, this is what you should indicate. For acidic reaction, this is what you should indicate. It's very, very important. Now, if you want to write the KB for this, what did I tell you concerning the dissociation constant? Only the species which change will surface. That means pure liquid and pure solid will not surface. It means this H2O here will not show. So what are you now going to have? KB will be equal to the concentration of the product side, which is this, all over the concentration of the reactant. In this case, this is the reactant. So these are KB. So you should be able to write the equilibrium constant expression for KB and that for the base. All right. For Ka. Now, the higher the value of Kb, the stronger the base. Of course, we said the higher the value of Ka, the stronger the what? The acid. Now, the higher the value of Kb, the stronger the base. All right. So that is that. All right, so that is that. Now, there's another way for expressing the degree of dissociation. The degree of dissociation can be expressed as Ka Kb, which I've actually explained earlier here. Now, the degree of dissociation can also be expressed as pKa and pKb. Is that okay? Now, when we talk about the pKa, what do we actually mean? pKa is another way of expressing the acid and base dissociation constant. pKa is gotten from Ka. pKa means the negative logarithm of Ka, while pKb means the negative log of Kb. Now, listen, the larger the value of Ka and Kb, the smaller the value, the larger the value of K and Kb, the smaller the value of what? pKa and what? pKb. So you may be asked a question. An acid that have a very high pKa and the one that have a low pKa, which is the stronger acid? Let's say you have two acids, one pKa1, pKa2. One has pKa of 10, while the other one has pKa of 2. Which of them is the larger acid? Or which of them do you think is the stronger acid? Now listen, the one whose pKa is smaller is the stronger acid, while the one whose pKa is higher is the weaker acid. Because the one whose pKa is larger, is smaller rather, have a very high Ka. And the higher the Ka, the more stronger an acid is. Is that okay? The higher the Ka, the more stronger an acid is. Now, if the Ka is high, it means the pKa will be low. Now, if the Ka is low, it means the pKa will be what? High. Because we said here that the higher, the larger the Ka and Kb value, the smaller the what? pKa and pKb value. Same thing is applicable to Kb and what? pKb. So you can actually see here. Now let's go to some calculation. Okay. Let's do some calculation briefly. Calculate the pKb for the basis. Calculate the pKb for the basis. Now, and arrange the basis in order of increasing strength. Here's my calculator. Now we talk about the pKb. All you just need to do is very easy. All you need to do, my dear student, oga show na now when they say calculate the pKb, all you need to do is press the negative log of the Kb. So we have ammonia and we are going to arrange them. Ammonia. So go to your calculator. This is my calculator. Are you getting it? Go to your calculator now. This is my calculator. Press. So you are going to have negative log of 1.8 times 10 to the power of minus 5. You must press it. What did it give to me? Equal to 4.74. So you have 4.74 as the pKb. This pKb of ammonia. Now the next one is acetate ion. What do you think is the pKb for acetate ion? Now you come back. This 5.6 for the 5.6 times 10 raised to the power of minus 10. This gave me 9.25. Now NO2 minus negative log 2.2 times 10 raised to the power of minus 11. That gave me NO2 negative 10.65. We've already arranged this thing before where we said that by order of base, NO2 minus is less than CH3COO minus, which is less than NH3. And you can actually see, we said that the higher the pKb value, the lower the what? The Kb value. And the lower the Kb value, the weaker the base. True or false? So you can see that ammonia has that of 4.74, while this one has that of 9.25, while this one has what? Around 10.6. These are the pKb. So it means that at the end of the day, this will have the higher pKa but lower Ka. I mean higher pKb but lower Kb, and then lower basic strength. So the basicity increases like this from here to here. That's how the basicity of this compound increases. Alright, so that is the correct answer to that question. Oswald dilution law and dissociation constant. Now, there's what is called the Oswald dilution law. Now, consider a weak acid HA of concentration C mole per dm cube. This is a concentration. Particular concentration mole per dm cube. And degree of dissociation alpha. Now, when we talk about the degree of dissociation, it's something that you must take into cognizance. Now, I really want to explain something here for you all to understand. Now, that is, if C is the concentration of a particular compound. Now the degree of dissociation is represented with what? Alpha. Now alpha can be considered as the fraction of the whole that dissociated. When we talk about the fraction of the whole, that means if you have the whole compound, what fraction of it dissociated? Is that okay?